what we just did was we just played with a network, the picture. Now this is another way to do it. Here is a way to work on a table. So what we just did was, it's called minimum cost method. So it's like you find the lowest cost every time, and then you load as much as we can there, and then you update, and then move on to the next lowest cost and until you're all done. Okay. So that's what we just did, and that's instead of playing with the picture, we could also, and picture is kind of nice because you kind of see visually what's going on. But the kind of more efficient way of doing it is with a table. So here's a table way. We're going to do the exact same thing now with a table. These are actually called tableaus, like French, like tableau, right? So it means table. Okay. So here is a summary of what we just did and what we're just going to do. And you could see here. Let's try to make a sense of what this table is saying here. So you can see here in the rows you have the plants. You have origins, the sources, the places that have the stuff, Cleveland, Bedford, and York. And how many do they have? Here, in the supply column, here it tells you how many are available, 5,000, 6,000, 2,500. And then in the columns, we have the distribution centers. That is the destinations. And how many do they need? In the bottom, you'll see the demand values here. So it's the same data. And also in the little boxes here, you see the unit cost. These little numbers are the unit costs we saw. And so what we do is look at all the costs, look at all the unit shipping costs, and pick the smallest number. Just like before. Okay, we know we did it before, so we know it's a 2. 2 is the lowest number. And there's more than 1 2. So you got 1, 2, 3. Just pick the first one. Just pick the first one. So you go over and say, okay, 2. Now Cleveland has 5,000. And Chicago needs 4,000, and like before, okay, 4,000 is how many we're going to send to Chicago. So 4,000. Now here we could kind of cross this out and put a 0 here, saying we're done. Chicago is receiving now everything from Cleveland. It doesn't need to receive from other places. So I'm gonna kind of cross out this column, or you could kind of just put X's here. So either way, it's fine. Or you could kind of highlight with the entire column. So it's something to indicate that you're done. You're done with this column, so you will not put more stuff in these cells. Okay. And then Cleveland has 5,000, now is sending out 4,000. So here, remaining supply is 1,000. Okay, is 1,000. So that's the first step. And then now we pick the next one, the next one, so forth. Okay, so next one we have here's a 2 we could work with. So here we have 2,000, 6,000. So what you're always kind of comparing the two values, and you want to pick the smaller value, right? So 2,000, 6,000, smaller value, put the 2,000 here. Then St. Louis is done. So that's, we cross out the column and say 0, remaining demand. And then the Bedford has 6,000 minus 2,000. Now it has only 4,000. Only 4,000. Okay. So that's the 2 steps, right? So let's see, what did we do? So this one, we did this one first, and then we went to this one. I mean, if you want to backtrack later, if you want to see what you did later, it's good to have like these little step numbers, so you could see. So 1, 2. Okay, now let's see. Here's another one, 2. So this one we're going to load stuff here, 6,000, 2,500. And what do we put here? $2,500, thank you. 2,500. Okay, so we're done with York. 0 supply here. And here is going to be 3,500. Okay, and then let's see. So that was number 3. Then we have 3, 6. Okay, so 3 is the first 3 over here. We're going to load here, and here say 1,000 versus 3,500. So we put 1,000 here. Then this part is Cleveland is done. Is now done, and then here we update. So each time you're going to update the column and the row, or the demand and the supply. Okay. and that's 3,500 minus 1,000 is 2,500. 2,500. Then what? Okay. Oh, right. 2,500 from Bedford to Boston, and that's all there's left, right? Let's see. Okay. Now, oh, what happened to Lexington? Okay. Oh, so that's the next step actually, right? So that's the 3. So now we have here 7, 3, and what else do we have? So we have 7, and then 3. That's it. 7 and then 3. The other cells are all crossed out. So we go. Let's go over here, and here we're going to put in 1,500. So that's done. And then we update this. 4,000 minus 1,500 is 2,500. Okay, so that's 1, 2, 3. That was number 4. And then now we go over here. 7. This is the only cell left. So no choice here. So here we put in 2,500. So that's done, and that's done, and everybody's done. Everybody's done. Okay. And what we saw was, 7 is a pretty high cost, right? 7 is a pretty high cost, and in the last step, 7 was the only choice we had, so we had to use it. We had to use that cell that has the most expensive cost, and that's why this doesn't always give you the best solution, because you're just worried about the next step in this method. We want to kind of do the best we can in the next step. We're just looking at the next step. We're not looking at the overall, the grand scheme of things. So we're just looking at kind of trying to do the best in each little step. So sometimes it's kind of like you're being short-sighted, so you might lose the kind of overall picture. And later at the end, you might be forced to choose a cell that's more expensive than others, because every step you take, you are eliminating lots of other choices. So every time you choose, you're eliminating other choices that could have been good, and at the end you might be forced to choose something that's not so good, like the cell that has a $7 cost. But this is if you don't have any other option, if you don't have a way to actually find the best solution, this kind of method is actually a very good method, and it's easy to understand, and it kind of follows a logical sequence of steps. Okay, so this is called the minimum cost method. And again, it doesn't necessarily find the best solution. It'll find a pretty good solution. So we call it a heuristic, and heuristic means basically like a rule of thumb. This doesn't guarantee the best solution, but it's a kind of good rule to follow. It makes sense, and it'll give you a pretty close to the optimal solution. So. This part is just a cleaned up part without stuff crossed out. So this is a solution we just have, and here is the calculation of the total cost. So this is the same solution we had with the picture. So the same total cost, 42,000. 42,000. Okay. Okay, so this could be the best one. We just don't know. There's no guarantee. There's no guarantee. So we don't know whether it could be the best. Sometimes we might get lucky and solution happen to be best, but we wouldn't know that if we were best, we wouldn't know unless we knew how to get the best solution, and then we could compare. So in this instance, we know how to get the best solution, because I'm going to tell you how to. Okay. So we're going to formulate this as a linear programming model to find the best solution. So you could see here, we're trying to decide on all these amounts. So we're trying to decide how many to ship in all these cells. So the amounts in these cells are your decision variables. So in our linear programming model, we're going to have decision variables that represent these amounts. So we're going to set it like this. We're going to set it like this one. We're going to call it X. Everything else starts with X. And as two subscripts for the row number and the column number. So like, this is 1, 2, 3, row 1, row 2, row 3, column 1, column 2, column 3, column 4. Okay, so we're going to say X, ij, and I is a row number, and j is the column number. So this one we're going to call it x11, 11. This one is x12, x13, x14. So that's how this is the kind of convention of naming the variables in this transportation kind of problem. And this one, what would you call this? X21, right? So 21. So row number and then the column number. So this is x22, x23, x24, x31, 32, 33, and 34. Okay, so it's straightforward, right? It's row number first, and then the column number. So the first index is the row number where the units are coming from, the supply points, and the second index is the column number where you have the demands. Okay. So here is a linear programming model. So x of I, j, that's going to be our decision variable. How many to ship? How many to ship from origin I to destination j? So amount shipped from origin I, that's I, to destination j. So how many will go from plant I to distribution center j? Yeah. Okay. So that's the decision variable. And the objective is we want to minimize the total cost. You want to minimize the total cost. Like here, how do we get the total cost? We have to go to the shipment, and so that's your xij variables. And then here you have the unit cost. So you got to multiply the unit cost by the variable, and then you add them all up. Okay, and so that's what we need to do here. So it's the unit cost times the variable plus unit cost times variable and so forth. You just keep doing it, and there's like 12 terms because there's three rows and 4 columns. So 3 times 4 is 12 terms. There's a big sum there, and you want to minimize that. So that's the total transportation cost, and the constraints come from the fact that we have limited supply at these plants. We have limited supply at these plants. So at each plant, you can't ship more than what you have. So for instance here, like here, if I add, so like here, in Cleveland has only these 5,000. So you can't ship more than 5,000. So when I say something like total shipped out must be less than or equal to 5,000. Okay, total shipped out from Cleveland. So if I add all this, that's the total shipped out. Right, so 1 plus 1 2 plus 1 3. So if I add up all these amounts, that shouldn't be more than 5,000. So that should be less than or equal to 5,000. So that's how we could write the constraint for each row. Okay, so it's kind of like this. If you add up all the variables for each row, and that's the total amount shipped out from wherever you are, that should be less than or equal to the supply. Okay, and then we also need for each column total received or shipped into. Total received must be the demand. So you gotta receive all that you demand. So you gotta, and Boston needs to get 6,000. For instance. So total received at Boston is going to be, amount that comes from Cleveland plus amount that comes from Bedford plus the amount that comes from New York. That must be equal to 6,000. So we go to each column and then add the variables, and that should be equal to the demand number given. Okay. Like this and like this. So those that's how many constraints. You got 1, 2, 3, and then 4, 5, 6, 7. So 7 constraints. So there is a 3 row constraints here, and then 4 column constraints. And so that's what it says here. Here are the row constraints, and here we have the column constraints.